Assalamualaikum warahmatullahi wabarakatuh. We are from Group 5. We'll be presenting our mini project which is entitled Analyzing Vibration in a Two Pendulum Coupled System. So this is our group members which is consists of 5 people, which is AIMAN HUSAINI bin AZMI, MARWAN MUSTAQIM bin HASIM, AHMAD DANISH AFIQ bin SUHARDI, NURIKMAL HAZIM bin AHMAD FIZDRI, and Muhammad HARIZ SIRAJUDDin bin Muhammad ZAIN. So I will be presenting the introduction part, which consists of background of study, objective, and scope of study. So our project is involved with vibration. So vibration is a widespread phenomenon in engineering, impacting design, performance, and safety of mechanical structure. So for 1 degree of freedom, we have the spring mass damper model, which is the simplest vibration system. So vibration, the oscillation of system, plays a pivotal role in engineering application. So our focus is on coupled system, where interconnected components influence each other. Now for our objective of study. So we have 3 objectives. So the first one is to investigate the dynamic behavior of vibration in coupled system. The second is to develop analytical tools and methodologies that fit the analysis of coupled system. And the third one is solving the mathematical model using the manual solution and computer aided solution. We're moving to the scope of study. So in this study, we're diving deep into the dynamics of coupled systems, specifically those with 2 degrees of freedom. Why two? These cases offer a fundamental understanding of how components interact. So, in essence, we aim to develop advanced mathematical models to describe the intricate vibration in these systems. This involves creating a partial differential equation using metric methods and employing advanced mathematical techniques. We are all about unraveling the complexity within the vibration of coupled system. So that's all from me. Now I will be passed to the next presenter.
Now we are on the part of the mathematical model. Before that, if you find my explanation is too fast, or maybe you wanted to look at the equation even longer, you may pause this video. So as for our model, we are using two simple pendulums coupled by a string, and each pendulum vibrating independently at small amplitude. So the coupled system has some normal modes of vibration given by F0, F1, F2, and Fc. And as for the coefficient, we have G, L, K, and also M, which is stated below. In our case here, we have angular frequency. Now look at the upper left corner there. We have omega 0 is equal to 2 pi f0. So as from the previous slide, we already know the equation for f0. So we just need to substitute it into the omega 0 equation. And then we will get the omega 0 equals to square root g of L. Then we do the same to make omega 1, omega 2, and omega c. As then we look at the lower left corner, we have the mathematical model for vibration coupled system with the initial condition as stated there. So we are on the formulating model. So we are going to change the coefficient into omega. So first we take the first equation, then we divide both sides with m and combine the same variable together. So number 3 is change the coefficient into omega, and number 4 is we repeat on the second equation, the same method. After we get the omega equation, we substitute the value of the coefficient inside the omega. So we will get this value of the omega. So lastly, after get the omega value, we substitute the value inside the mathematical model there. So we will get as stated there, and also with the same initial condition which is stated there.
So we will use the matrix method first, because it is a second order differential equation. We let u1 is equal to xa and let y1 is equal to xb. And after some manipulation, we get a 4 by 4 matrix for the coefficient matrix, where u1, u2, u3 is the solution. So using the matrix method, we get the eigenvalue is plus minus I square root 3 and plus minus I, and the corresponding agent vector to the agent value is given by V1, V2, V3 and V4 here. So we solve by using the matrix, and because the the solution to the system of ODE is also a matrix. So at the beginning we said that the U1 is equal to XA and Y1 is equal to XB. So for the each row is given for the first row of the solution is the our XA equation, and where for the third third row is the XB equation. So after we use the initial condition, we get that the coefficient is A is equal to 3 over 2 square root 3 and B is equal to 1 over 2. So after that we get that XA and XB.
Assalamualaikum. My name is AIMAN HUSAINI bin AZMI, metric number 2116177, and today I'm going to continue with the computer aided solution. So our group is solving the system of ordinary differential equation using the matrix method. So here on the left you can see that I'm using the uh, coding from programming tool MATLAB. So as you can see on the left side, you can see the coding that is defining the function for our problem to obtain the exact solution. Next, on the bottom side is the coding to solve our system of ordinary differential equation using the built-in function ODE45 with specific value of the variable. Plotting the graph. Next, this is the coding that used to plot the graph for both numerical and exact solution. So the graph below the coding shows numerical solution and exact solution on the same plot for each case. So the straight line is for the numerical solution and the dotted line show the exact solution. As you can see, the numerical solution is approximate to the exact solution.
Okay, now I will explain about the last part of our project, which is conclusion and recommendation. Before that, my name is Muhammad SIRAJUDDIN bin Muhammad ZAIN with metric number 2112979. So for the first one, relating to our learning in this subject, the solution of analyzing vibration in two pendulum coupled system use metric method in order to solve ordinary differential equation. We use a method of solving homogeneous linear system with constant coefficient in order to get the manual solution. Compared with the manual solution, computer-aided solution give more precise answer using MATLAB. So for the conclusion, the first one is frequency of independent pendulum motion. The frequency F0 of the independent pendulum motion is determined solely by the length of the pendulum L and the acceleration due to gravity G, as given by F0 equals to 1 over 2 pi times square root of G over L. The second one is normal mode of vibration. The coupled system exhibit two normal mode of vibration, F1 and F2, with frequencies determined by additional factors such as the spring constant K and mass M. These frequencies provide insight into the complex interaction between the pendulum and the connecting spring. And the third one is angular frequencies. The angular frequencies omega 1 and omega 2 corresponding to the normal mode are derived, emphasizing the impact of both gravity and the spring constant on the system behavior. So, for the next part is recommendation for model improvement. The first one is including the damping effect into the model. Introducing damping term in the equation of motion would enhance the model realism, as the real world system often experience energy loss due to damping. And the second one is extend to three-dimensional system. Consider expanding the model to represent three-dimensional motion, as it would be more representative of complex physical system. So that's all from us. Thank you.